Hey everybody, Dr. A here, and in this video we're going to be providing some background information on what is known as flexural stress. So what is flexural stress? Well, flexural stress is also sometimes called bending stress. So if you ever hear the term bending stress, it means the same thing as flexural stress. And it's a type of normal stress, which means that it's perpendicular to a member's cross section that develops due to a bending moment M. So one way of saying it is what I just verbally said. The other way is what I wrote here. It's a type of normal stress that develops in a member's cross section due to a bending moment M. Okay, so let's go ahead and draw a little figure that corresponds with this. I'm going to start with a beam segment. Okay, and now this beam doesn't have to be simply supported. I'm just drawing it as a simply supported beam. But it could be any kind of beam. And I'm showing a thickness here, a beam thickness. Now let's say that we have, some applied loads here, F, and maybe some kind of distributed load, W. Okay. And what's happening is this member is going to tend to bend, okay? And so it's going to kind of bend and deflect like this. Okay, that's exaggerated, but it's going to tend to bend and deflect something like that, all right? Now, here's what I'm going to do. I'm going to kind of zoom in a little bit, and I'm going to do a little bit of method of sections technique here, okay? So let's say that I zoom in and I do a little method of sections technique. So what I'm going to do is zoom in quite a bit, and I'm going to show the beam thickness here. And I'm going to put a dot, 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 just to indicate that, hey, the beam could keep going on over here. I don't really care. And I'm going to draw a little cut section here. Okay. Now, when I draw my cut section here, of course, we do have a shear force that's going to develop here from internal loading, and we're going to have a bending moment that also develops. Now, for the sake of clarity, I'm only going to draw the bending moment, okay? But remember, this is a flexure member, this is a beam, and so there is a shear force here that's going to develop as well, but I'm not going to draw it just to keep the figure from getting too cluttered, okay? Now, we have this bending moment that's developing in the cross-section, and this is, an internal bending moment. I drew a little gap here on purpose, and you'll see why in a second, okay? Now, let's say that the member has a neutral axis right here, okay? Now, this NA, what does NA mean? Well, neutral axis, the abbreviation for it is NA. This is defined by where the member's centroid is located, okay? So let's go ahead and say that the member's centroid is located right here. And if you remember from previous knowledge, we call that Y bar, okay? Y bar, or the member's centroid, okay? And now specifically, I'm going to call this Y bar sub B for bottom. Now, you remember from your previous knowledge from statics, you could also define it up at the top as Y bar, but we would call this Y bar sub T for top. And that just means that this Y bar is measured from the top surface, and this little b right here just means that Y bar is measured from the bottom surface. That's all that means. And you remember how to get centroid from previous knowledge. Now, what happens is whenever you have this internal bending moment that's developed, it's causing a type of normal stress, okay? And that's what we call bending stress or flexural stress. So what happens is it's going to develop this normal stress that's going to have a shape kind of like this, okay? It's going to have a triangular shape. Okay. Now the stress distribution is normal to the cross section, which means that when you draw your little vector symbols, they need to be perpendicular to the beam's cross section. All right, so the way this bending moment is acting, the way I drew it, we're going to have compression above the neutral axis. Now, it's only compression above the neutral axis because I drew this bending moment vector such that compression is the compression zone is above the neutral axis. The bending moment is causing the top portion of this member to be compressed. And then similarly, but in the opposite sense, we're going to have tension below the neutral axis. Okay, so I can call this little zone right here the tension zone, and I can call this little zone above the neutral axis the compression zone. Okay, but it's only because I drew this bending moment in such a way that I'm showing compression in the top portion. Okay, so this is a side view. I'm going to make a note here. This is a side view in 2 dimensions of what you could see develop somewhere along this beam. Okay, now the question becomes, what are these values? How do I actually calculate these values of stress? Because at any point along this distribution, we're going to have a stress value, okay? At any point along this distribution, this whole distribution represents a stress value, but it's varying, okay? So this is a linear stress variation. So the question is, how do we calculate that stress variation? Well, we have a simple formula that we use, okay? It's going to be sigma equals, and it's going to be equal to my over I. Okay, very simple. Now, this m is the same moment that we're talking about here. It's the internal bending moment at that specific spot, at that section of the beam, all right? So I'll make a note here. I'm going to say m equals the internal bending moment. Now, how do we get this? How do we get m in general? Well, we've studied that already. We can say we get it by method of sections or by drawing the moment diagram. Okay, so m is just the moment that at a spot, at a location on our beam that we can obtain by either method of sections or eventually getting a moment diagram. Okay, so that takes care of m. All right, what about y? What about this term y? Well, y, I'm going to change colors here. Y is the distance above the neutral axis to the point of interest in the beam's cross section. Okay, so let me write that down for us. Y is it's a vertical distance above the neutral axis in the cross section where we want to compute sigma. Okay, that's what y is, and we're going to talk a little bit more about that here later in the video. All right, now what about I? I is the moment of inertia about the centroidal bending axis. Now, for our purposes, most of the time, this is usually going to be I sub x. Okay, so we're going to say usually I sub x. But remember, depending on what the problem asks and if you have a weird loading situation or, you know, a professor is trying to trick you, it might not always be I sub x. Most of the time in mechanics of materials and structural analysis, it is I sub x. but it's problem specific. In general, it's the moment of inertia about the centroidal bending axis. Okay. Now, again, you got I. You learned how to calculate I in a previous class, like in statics, for example. All right. Now, this is how we calculate sigma in general, okay? Now, the question becomes, what if I'm interested in a maximum value of sigma, okay? Well, if I want a maximum value of sigma, which is often what I'm interested in, I need to look at the maximums of m and y, all right? So let's make a note here. For sigma max, we use M max from the moment diagram or method of sections, but most often it's from the moment diagram. And we use Y bar, okay? So for example, if you want maximum bending stress, that's going to happen at the extreme fibers of the member, okay? So this value right here is going to be sigma max sub t for top, and then this value here is going to be sigma max sub b for bottom, okay? So for example, if I want sigma max top, I'm going to use the maximum moment from the moment diagram. And then for y, I use y bar top, okay? What if I want sigma max bottom? Well, I use the maximum moment from the moment diagram, and then I use y bar, which is measured down to the bottom, okay? So that's what we're going to be interested in more often in a mechanics of materials or even a structural analysis class, is the maximum values, okay? So I'm going to say, make another little note here, sigma max occurs at the extreme fibers of the cross section, okay? So we can say sigma max is going to be equal to M max times Y bar over I, okay? And again, remember I is usually going to be I sub X, all right? Now, whether or not you want it at the top fiber or the bottom fiber, that's where you will use either Y bar top or Y bar bottom, okay? Now, the next thing you need to pay attention to is if you have tension or compression, okay? So in what I drew here, again, the compression zone was above the neutral axis and the tension zone was below the neutral axis. But if the moment was going the other direction, then these would be reversed. You would have compression on the bottom and tension on the top if the moment was reversed in the other direction. So you got to be very careful with stuff like that, okay? And that will affect whatever you might want to call positive or negative, all right? So some people like to say positive is tension and negative is in compression, all right? Now, where is the bending stress 0 in the cross section? Well, that's going to be at the neutral axis. So we're going to say sigma equals 0 in the cross section at the neutral axis, at the NA. Okay, now here's what I'm going to do. I want to draw a 3D version of this figure just to give you an idea of what this looks like. So I'm going to say in 3D for a rectangular cross section, what would we be seeing? So here is a nice 3D depiction of what we could be seeing. And again, for simplicity's sake, I'm going to draw a rectangular cross section, kind of like that. All right, and then I'm going to draw some centroidal axes here. I'm going to call that the centroidal x-axis, and this is the centroidal y-axis. All right, and so the neutral axis, is basically this set of axes and going right through the middle, because it's like a rectangle or a square, okay? And if I draw, you know, a bending moment that's, let's keep it consistent with what I drew in 2D. If I draw it, you know, out here somewhere, here's M, then what is this stress distribution going to look like? Well, we're going to have compression along the top. Okay, and this is going to linearly decrease down to 0. So at the top surface, we have this compressive stress distribution, and it linearly decreases down to 0 here at the neutral axis, okay? And then it's going to increase again, and it's going to be in tension when we are below the neutral axis. So tension like this. And again, this is 3D, okay? So this is like a 3D figure, all right? So this is the general distribution, and again, we can label these dimensions. This is y bar bottom, so y bar sub b. This will be, I'll draw this a little bit better. This will be y bar top here, and down here along this edge we have sigma max bottom, and then up here along this edge we have sigma max top. All right, and then at any point, if you want the stress at any point, any intermediate point, you use an intermediate value of y there. Okay, so this is not my best artwork. I'm not the most not the most talented when it comes to drawing things, especially in 3D, but this is it in general. Now, another version of this formula that you can utilize is the following. So we're going to say S is defined as what's called section modulus, okay? Now, S is generally going to be defined as moment of inertia divided by y bar, okay? So you can have, so for example, I'm going to say e.g., for example, S sub x top would be I sub x divided by y bar top. S sub x bottom would be I sub x divided by y bar bottom, and so on. So if you take a moment of inertia value and you divide it by a centroidal distance, you get this thing called section modulus. So in some areas of engineering, you base things off of section modulus instead of moment of inertia and centroidal axis. So one way you can express the bending stress equation is instead of you know my over I, you can say sigma max is m max over s. Okay, and so this is another version of the formula that we're gonna explore and utilize sometimes, but this is for the maximum case, because when you think of section modulus, it's specifically based on the centroidal axis, the location of the neutral axis specifically. It's not for an intermediate value, so that's why we see this as sigma max, as m max over s. Okay, so this is another version of the maximum value when you're interested in the bending stress at the top and bottom fibers of a member. Okay, so that concludes this background video on flexural stress, or also called bending stress. If you found this video helpful, please hit like and subscribe.